So how does the circuit operate? So the circuit has, like I said, three sections. One is the oscillator section, and the other section is the output of the oscillator section is fed into the duty cycle control. And from the duty cycle control, we're gonna buffer the output of the duty cycle control, and from there we're going to put it into a level shifters circuit where we can basically arbitrarily use any supply voltage that we can use for our anything that we're basically let's call it our plant that we're controlling. In this case, it's a DC motor. In fact, the output buffer can be replaced by an optocoupler. Let's say if you wanted to control something that you want a complete isolation from the control circuit, you can feed this into, say, an optocoupler of some sort. That optocoupler would basically give you the required isolation, galvanic isolation between the output, the actual plant that you're controlling, from the control circuit, which is a low voltage side. Basically, you can do that where you can isolate the two grounds, and you can apply that in that case. So that's one of the other applications that you can use it for. So it's very flexible circuit. Now you can buy PWM chips that you can use in your circuit, but this is highly flexible because if you use high voltage transistors, you can scale this up to any voltage level that you desire for your application. So let's talk about how we generate the 0% to 100% PWM control. So we'll start with the oscillator section. So in the oscillator section, if we put it if we talk about the oscillator section, so in order for us to generate a PWM signal, what we need to do is we're going to generate a ramp voltage, basically a ramp voltage. This ramp voltage will be controlling the width of our PWM. So, and it's going to oscillate between a minimum voltage, Vmin, and Vmax. So based on where we choose on this ramp voltage, based on when we turn on our control, we can get any number of width of square wave that we can use, right, for our PWM signal. So if we choose this, we have this width, right? That width will give us basically our duty, right? So if we choose this, that'll give us the other width, right? And if we choose this, that will give us the other width, right? Duty cycle. So basically that's how we're gonna do it. So how are we gonna do it? So one easy way to do it is just to use a constant current, right? You feed a constant current to a capacitor from a supply from VCC, I, C. Then if you use this output here, VC. So the capacitor equation IC equals C dVC dt becomes a linear relationship such that the generated voltage VC is basically a constant, basically a linear ramp from a specific value to a specific value. So that's how we can generate. That's a very simple way of generating a linear ramp signal that we can use for our duty cycle monitoring or control. So once it reaches a specific level, what we have to do is, because then the capacitor will charge to whatever maximum compliance voltage of this current source, then we have to reset, right? We have to reset it with a switch, right? Well, whatever switch. This is switch. This switch will basically reset the capacitor, right? Discharge it to ground, and will begin again, right? The charging cycle will begin again, right? So that's how we do it, right? So this is the simplest way of to generate a ramp signal that you can use for your PWM control. So how are we implementing the current source, the switch is what I'm going to be going over next. So here's our circuit again. So how are we implementing the switch, the current source, and of course, which one of these capacitors is the capacitor that's generating the linear voltage? So as you can see, this is the capacitor that I'm using to generate the linear voltage, and that capacitor is being fed by this current source here. This contraption here sets the output current, and that current is generated by this resistor here. That resistor is across this base to emitter junction of this transistor. So the current on it will be the base emitter voltage divided by whatever resistance we set here with this pot. And that current will flow this way down into the capacitor and generate that linear ramp. Now, when this ramp reaches a certain value, we're going to switch it to ground using this back-to-back connected PNP and NPN transistor configuration here. This is actually, if you look at this closely, it's a device, it mimics a device called an SCR, basically a gate triggered diode, basically. And what it does is when this capacitor reaches a certain value, it's going to turn on this transistor and then turn this transistor on again. And then through a positive feedback, both transistor will turn on really hard and pull this voltage here to ground. And once the voltage is near ground, this circuit is going to run out of current and it will automatically shut itself off, thereby allowing the capacitor to charge back up again in a linear fashion from this current source. Now, this switch here, if I actually draw it here, so what we have is, we have an NPN transistor that's connected to a PNP transistor back to back like this, right? That's what we have here. So this is where ground is. This goes to the capacitor, right? Now I'm not going to draw the current source fully, so I'm just going to draw it like that, right? And then this is C. This is our output voltage VC that we're using to generate the ramp voltage. So what happens is when this capacitor reaches a voltage level that is above the reference voltage here, so I'm going to call this ref, Vref. So when it reaches above Vref 0.7 volts or VBE, right? Above that, right? Then this transistor will turn on, right? It's going to turn on and pull current this way. Now, if pull current this way, what happens is, right? Because now it's this VC is above Vref by 0.7 volts, right? So now current will get pushed this way. Now, if current gets pushed out of the base, then of course, proportionally, collector current is going to come out this way. Well, so what happens if there's a collector current out of this? Then that collector current feeds the base of this transistor. Now, if this transistor has a base current, then it's going to pull current from its collector as well. So what happens is basically more current comes this way, more current comes this way, more current comes this way. So this whole circuit goes into a positive feedback loop whereby both transistors get turned on really hard. They pull this to ground, close to ground, actually close to VBE of this guy, plus the VSAT of this guy, right? So the capacitor will actually get discharged. The VC will go down to its VC minimum. Will go down to VBE plus VSAT. VSAT. So it's approximately about 0.8 volts. That's what it's going to go down to. And when that happens, then there's no enough current to pull from here. Although there is current from this way, there's no enough current to sustain the positive feedback here, and automatically, automatically these two transistors turn off and the capacitor starts charging. Now, how am I generating my VRF? My VRF is just simply of a capacitor, resistor divider here. So I have 1K here, 1K here, and it's coming from my VCC, which is 5 volts. So that is fed. I could feed it directly to here, which will give me 2.5 volt reference, right? So, but I don't want to, if I do that, sometimes the circuit doesn't oscillate properly, like it doesn't start, right? The oscillations doesn't start reliably. So in order to, for the circuit to start oscillating reliably, what I do is I buffer this through an emitter follower transistor like that. And I connect it like that, as you can see, right? Through an emitter follower. This emitter, this is my, by the way, these are incorrect. So I'm using 1K, 1K. And I'll tell you why it's not 10K. Right? So 1K, 1K. And they get buffered by this emitter follower or common collectors transistor. And they go into that node here, which is going to be pulled down to ground, right? So that's where my reference voltage is coming. So my reference voltage is 2.5 volts, and I'm going to go down by a diode drop into here, and then go back up by a diode. So in fact, this voltage and this voltage is at the same potential, close to the same potential. So 2.5 volts, 2.5 volts, that's where the capacitor is going to charge to. And I'm actually not using a 1 nanofarad capacitor here. I'm actually using 33 nanofarad capacitor here. This circuit can operate into high frequency. Actually, I've tested as much as using the 1 nanofarad capacitor and a minimum resistance here about 100 ohms. A maximum of about 1K. So I've tested this to about 500 kilohertz. So this reliably can generate a very sharp PWM signal and up to 500 kilohertz. So that's really nice actually. So basically, so we mentioned how the oscillator works, you know, the reference voltage, that reference voltage gets buffered. Now this is very critical, this buffer here, this common emitter, because this node here is a high impedance node, right? And if we load it by this directly here, load it like that, it might not start to oscillate properly. So this buffer is there to make sure that this circuit reliably starts and oscillates every time you turn it on. Okay, and my current source is very simple. It's just back-to-back connected. So this current source is, we just kind of draw it here. So basically I take a resistor and I feed it into here. I drop, this is my VCC, which is 5 volts. It's a pot, so I can get variable current that allows me to trim my frequency, right? If I vary the current that's going into the capacitor here, the charging current, this charging current, then I get variable frequency, right? So I can trim my frequency to whatever value I like. Like I mentioned, I can trim it all the way from about 10 hertz to 20 kilohertz in this application based on the component values I have here. And so to generate the current source, it's just simple back-to-back connected PNP transistors. And I take this, I do it like that. Now this collector output is where my current is going to get out, IC, right? And that is going back into here, like that. And then my reference current flows into ground from using this 820 ohm resistor. This 820 ohm resistor. This is a 1K pot, right? So that's what it basically, again, this R, I'm gonna call it R pot P. So the current through it is IC is approximately equals to, this is VBE divided by RP. whatever RP is set to, right? So that's what you get. So this is actually nice current source where a supply voltage is not involved. If you increase the supply voltage here or decrease it, it's not going to affect that much the output current, which is the current that I'm using to generate the charging current into the capacitor here. So that's one section. So what we mentioned right now is we've gone over how we designed the oscillator section. So now that's how the oscillation works. Now I'm going to mention in my next video the duty cycle control. Okay, take care.